Hey, good morning, everyone, and welcome back. Hope you had a good night, and we're excited now to kick off day 2 of decoding. And welcome. That's my doppelganger. Yeah, that's my my virtual self that I've created. So yeah, welcome. We're going to start off with what's that? Well, we're working on. That's why we have a linguist on the squad here. We're starting off today with Gašper Beguš, the linguist for CETI, and will tell us about AI as a tool for discovery in animal communication. Take it away, Gašper.
Thank you so much. Okay, so thanks everyone. It's a pleasure to be in this workshop, third so far. So I want to talk about AI as a tool for discovery in animal communication and how AI can help us find new things. I also want to talk about the things we called coda vowels in whales. AI helped us to discover that whales have vowels. And I also want to present something very new that is not even in preprint yet, which is that those vowels don't only look like vowels, but also behave like human vowels. So we understand the world around us pretty well, but there are still many things to be hopefully discovered. And maybe for the first time, AI is so good that we have this non-human intelligence that we treat as a tool for new discovery in science. So we want to, as I mentioned, want to talk about how AI can help us with discovery, how humans are still needed in the loop. I want to talk about the vowels in sperm whales, and then also how those vowels behave like human vowels. So let me start with this exciting question, which is basically there are two questions playing out in science right now that are very, very similar, but a lot of people don't connect them. One is are humans just extremely smart animals? So if you increase the brain capacity, language arises and our intelligence arises. We heard from Professor Gopnik that there are many intelligences, but like the idea is scaling up our brain power did that cause language to emerge? And there's another debate in AI, which is if we're going to increase these models, are we going to get the human level performance, intelligence, or not? So studying animals and artificial intelligence kind of together is quite interesting, and what I'm going to argue can inform us on all sides. So there are mutually intelligible, mutually informative intelligences that we now work with, humans, animals, and machines. And some of the questions that we've been asking are very, very similar, right? So people in the animal communication world have been asking whether language is just scaling, result of a byproduct of scaling of our brain power, or is something specifically human needed for language, right? And the same again, we all talk about, oh, is our LLMs going to get to human level performance, or is something that we're missing that is human specific? Before we can get to whales, let me tell you how we in the lab approach this problem of dealing with something so unknown as sperm whale communication system. And the first thing we did is we tried to create more realistic model of human language, okay? So we know LLMs are great and everyone talks about them, but we're basically doing something in parallel. We're building models that are more realistically, more ecologically plausible, okay, more realistic. Because no baby learns from text, no baby learns from massive amounts of texts. No baby learns without speaking and listening, okay, that's a crucial. We learn language by speaking and listening. Without speaking and listening, you don't learn a language. And we have communicative intent. We speak to parents, and so do whales, right? Whales communicate with each other. So how is language produced? I have some information right now in my head. I'm encoding that into muscle movements. The muscle movements, as I'm sending air through them, result in sound. That sounds travel to your ears. Your ears turn sound movement, sound vibration into electrical signal, and you hopefully decode the same information as I had in my mind. Okay, that's how we're communicating. And so we're building with deep learning a closer approximation to that process than LLMs are, okay? And we love GANs. I really like the GAN architecture because GANs are generative adversarial networks is a family of deep learning architecture where the network learns by producing and perceiving or discriminating between real and fake data, okay? So the point is we're building closer approximation to human language process than say LLMs or other approaches. And we even actually give our models representations of mouth, so they have to move tongue and lips and so on. And there are several advantages of this. So we've shown over and over again that language can be modeled with this approach. Now, we have this completely unsupervised artificial baby that we developed in the lab, right? So the baby needs to learn human language. It doesn't know anything about anything we linguists think is meaningful in language, right? It's just a deep neural network architecture. It needs to learn by producing data and perceiving data and encoding information, just like you and I did right now when we're communicating. And we're basically giving it nothing, no information about language whatsoever, okay? And we've shown that this all-purpose pattern discoverer learned a lot about language. You can, you can model syntax, phonology, all sorts of things that we linguists think are important in language with this model, okay? Now, what is crucial for discovery using AI is that we understand these models, okay? We've been talking a lot about black boxiness and how we don't understand AI, which is true. But what we try to do is look inside these models. Okay, we have an artificial language learner, and we try to look inside it to see what it had learned. Okay, and we have this technique where we can have this giant artificial network of artificial neurons, and we find a single neuron that represents something that is meaningful in language. Okay, what are some meaningful things in language? Sounds are meaningful, like a sound like S is meaningful, words are meaningful, all these things, right? All these things that we're eventually gonna try to find in whales, right? You see what I'm getting at, like, we need to understand what is meaningful in whales. Now in language, I can play with these artificial babies because I know what is meaningful because I'm a linguist and I've been studying language for centuries, and I can always ask you, what are the words of your language? And you can tell me. But in whales, of course, that's not possible. And so we find this is the last layer of a deep neural network, okay? It has very few variables, and we find a single variable that corresponds to something we know is meaningful in language. And what we found is that we have a causal relationship between that single variable. We take one variable, we stretch it to extreme values. This is a little technical, but the point is we take one artificial neuron, we tune it to extreme value so that it overrides all other neurons, and we observe a causal relationship between, a sound S, which we know carries meaning in language, and this single unit. Okay. I take a single neuron and take S in and out of the output, right? There's a causal relationship between something that I know is meaningful in language and that single unit. These networks are really cool as well because they're highly, highly productive, okay? They start saying new words, although they never heard new words before. So this is, again, a property of the so-called GANs. They're one of the most interesting architectures because they're extremely productive. They need to learn not by just copying data, replicating data. They need to learn by imitation and imagination. That's what they do. And for that reason, they're very productive. So we train this artificial baby language, and it learns to imitate speech very, very well based on only hearing speech. Okay, we don't give any instruction to the network. And it also starts to say new words that it never heard before. Start. It says start, although it was trained only a few other words, none of it just start. So the idea is we have this very productive artificial model of human language learning, of artificial human baby, that we can look inside and show, look, it had learned something that I as a linguist think is meaningful. And I can do that in a causal way. And by the way, these models are really interesting. We can show that they learn like humans, that they have similar steps like humans. They even process sounds in a similar way as humans process them in the brain, because these are convolutional neural nets, not transformers. And convolutional neural nets are slightly more biologically plausible, and they were basically biologically inspired. So we have this good model of human language learning. And so what we did is basically, which is a all-purpose pattern discoverer, right? It finds something that is meaningful in language. And the idea is, let's try to test if it'll find something that is meaningful in whales as well, right? So the important thing is we need to know how to look inside the network. So this is the so-called AI interpretability, which is so popular these days, but it's very hard. I mean, we have a few techniques, other people have a few techniques, but it's a very, very, very difficult question and problem to crack. Okay, so I'm going to talk about two preprints with the team where we tried our artificial language learner and tested it on whales. Okay, we said instead of learn language, we told it learn whales, learn to imitate whales informatively, right? So what it has to do is it has to learn to encode information into their sounds, not into our sounds, right? Because if you think of what whales are doing, presumably they have some information just like I have. They're encoded in that information in codas, and another way is a whale is decoding that. Okay, so it's a very similar purpose. We said, okay, our artificial language, baby language, needs to not learn language now, but learn codas, and it needs to transmit information through this channel. So these are the sperm whales, and presumably they exchange information. I mean, the nice thing is that they communicate before hunting and while socializing, so there's a high potential for that there is actually some referential information going on there. And it was considered that, this is like a Morse code communication system, right? So only the timing between clicks and the clicks themselves matter. And so when we trained our model, actually something else showed up as informative, okay? So before training the models, most of the work claimed that the important thing in sperm whale communication system is the number of clicks and timing between clicks. And Sharma and al. Recently showed that there's even more complexity than the traditional schema, that there's tempo and rubato and all these properties, but still it was considered that the main unit is just clicks and their timing between them. Those are examples of a couple of codas, right? Different types. 1 + 1 + 3. We know that type pretty well these days. And another one, right? So we train our artificial baby language learner. We looked inside the networks and asked it, what did you learn? Okay, tell me, what did you learn? We use this technique where we take a single neuron inside this artificial neural network, stretch it to extreme values, and observe what will show up. And to our relative surprise, so the first thing that showed up, of course, was nice, because our model showed that timing matters and that the number of clicks matters, which is great because it's validation of something we already knew. But it also showed that spectral means and acoustic regularity are important. So basically, this artificial baby learned to imitate whales and exchange information through codas, and it used spectral properties to exchange information. So that doesn't mean that spectral properties are meaningful, but it means it's a good candidate. Okay, so this is how AI interpretability doesn't give you an answer, doesn't give you a final answer, but it tells you, where to look for it, because there's a high chances of something informative being there. Okay, then we went and checked and found something that is strikingly similar to human vowels. Okay, let's go back to humans a little bit. How do we speak?
So in this picture, there are two people. I think apparently they're both women. The one on the left is a little girl, and the one on the right is...
Okay, so what you have observed is we speak pretty fast, right? We move our tongue when we speak pretty fast. This is a person in MRI continuously scanning and speaking. So we have vowels, and we say vowels like a and e. And how exactly we produce vowels is quite interesting. So we send air through our lungs, and they hit vocal folds. And if vocal folds are just right amount, just in good tension, they will start vibrating. Okay, so when you this is me saying e, and e. Okay, you see these vibrations. Each of this period is one flap of a vocal fold. Okay, so our vocal folds will flap very fast. When they air passes through them, they start vibrating. On top of that, we have a vocal tract. Okay, so each of this period is a flap of a vocal fold. Now, the reason why a and e sound differently is because for a, I open my jaw a lot, right? A. And for e, I have it much more close, right? The tongue of somebody saying an a, the same person, you see that much lower here, and the tongue here is much higher. What this does is it changes the shape of this resonant body. Now, this change of the shape of the resonant body results in changes of resonant frequencies. And you see these dark bands on spectrograms, which is analysis of the sound. You see these dark bands forming. When I say an ah, the bands are close together. When I say an e, the bands are far apart. Okay? So that's how I know I can hear ah and e, I can produce them. And so that's how it works. The important thing is there are two separate ways there are two separate mechanisms that work here. One is I flap my vocal folds, and then I basically use a resonant body, just like church organs. They have long tubes, they have short tubes, and that creates different resonant frequencies. I change my tubes, the shape of this tube, so that I get different spectral patterns, and that's what you decode to get information from me. So these are the bands. These bands of frequency will be very important throughout this talk. So if there are any questions, let me know. So on the surface, whales' clicks don't look anything like vowels, right? So here are two codas, click 1 + 1 + 3, 1 + 1 + 3, and they just look like clicks. But the important thing that helped me find this pattern is that the idea that maybe their timing works differently, okay? Maybe their timing is just, these are big animals, they have slow heart rates, maybe they just have completely different timing. And this is something that the elephants have different as well, because the famous elephants have name talk show that there's, the elephants have names, but they respond to names much, much, much slower than we do. So that got us thinking. And so we started doing a trick which kind of makes these codas look more, basically easier for us to interpret. So what we did is we just simply started cutting time between clicks. Okay, something that doesn't look at all like vowels. We just started cutting the silences with the idea that maybe their timing just worked differently. And when you do that, the exact equivalence to human vowels starts appearing, because you see these bands of frequencies now start forming. Okay, so now, just like human vowels have, we saw those periods up and down that represent flaps of our vocal folds, and then bands of frequencies. In a very similar way, this is probably better to watch on the screen because spectrum is not well represented on these projectors. But we see a clear, distinct, and seemingly really controlled pattern where some vowels have a single peak, some vowels have two peaks, and we'll see there's a lot of other patterns as well. But the cool thing about this pattern is that you can hear it with a naked eye. The first click is one type, the second click is the other. You hear the difference? So no clustering needed, no PCA, no fancy algorithm, just take timing away. And if you put together the whole conversation, this is roughly how it sounds. Okay, this is our timing and their communication system, I think. And that's not just one whale. This is Fork. This is Pinchy, by the way, the grandmother that is very chatty, and all the cool stuff was for discovered with her. But other whales have a very, very similar recurrent patterns where there's this control. And note that when this is our codas, right? So there's a little bit more space between codas. If you're a coda, you're only one type on the other. So this is not some sort of continuous holistic sound. This is really discrete, looks really controlled. Okay, we have another thing we call diphthongs. So humans have vowels and diphthongs. So vowels like a and e, but diphthongs are like I and ow, where you combine a few vowels. So what we observe, probably also better to watch on the screen there, is that sometimes this A-type vowel, so there are two types we call the A-type, the A vowel and the I vowel. The I vowel has two peaks, A vowel has one peak. So sometimes the A vowel has this really pronounced patterns of trajectories, right? So the first coda here you see is very flat, but then the second coda has like first low click and then high two and then goes down, and this one goes up. And we correlated with this with movement, and it's the opposite what you expected, right? So this one that has flat coda, flat frequency, flat band, has a lot of movement. The whale has moved a lot, whereas these two have very little movement. So this is likely not some artifact. And we see this pattern over and over again recurrently in cross whales. Like this is extreme case of Nalgene having this pattern. So they're beautiful, beautiful patterns that could potentially carry meaning, right? So you see these spectral properties and their movements. So these cool patterns emerge. Now we need to understand how they arise, right? How whale produce them. And actually, this is extremely similar, right? So remember I told, when I say an ah, there's a bunch of flaps of my vocal folds, and each of this period represents one flap. Well, it turns out that clicks are just flaps of their vocal folds. And then on top of that, they create these spectral patterns. So they're similarly two distinct mechanisms. They click, and they have the spectral patterns. And so this is how we frame basically their communication system now with what phoneticians framed our vowels and our consonants 60 years ago in terms of the so-called source filter theory, which is the source is our vocal folds, which produces the basis of vibration. And then on top of that, we filter those frequencies with our changing resonant body, which is our vocal tract. And the equivalent of, say, vowel duration, we have short and long vowels like E and E in English, like pit and peat. The number of clicks is roughly equivalent to that, or the duration of the coda. And then something we'll see very similarly, the different coda types can be kind of understood as our tone, right? Some languages have tones, like Chinese, and 1 + 1 + 3 coda, so click, 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 versus click, 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 is basically an equivalent of different tones in Chinese. And then the filter properties are vowel, different vowels, vowel height or backness, and form and trajectories, and the equivalent of that is diphthongal codas or coda vowels. So this can be really, really interesting, piece by piece paired with something like Mandarin, right? So in Mandarin, you can say a ba, or you can say a b, but you can say ba and b, or b and ba, right? So this is
Ba.
Ba. You see that the rate of this click, okay, these are now vocalic pulses, right? These are vocal fold vibrations. So if this is a human vowel, but in whales, this would be clicks. It would be just a bunch of clicks. You see, the timing between clicks is decreasing. So when I say a ba, ba, my vocal folds start clicking faster and faster, okay? And on top of that, I have the ah band here, okay? So two different, right? So the timing of my clicks and then spectral properties, the rate of vocal fold vibration, and then the way I change my vocal tract, right? Ba, bi versus ba, ba. So two, now I can cross these properties. This is the same syllable, but with different tone. Now what you see is that here the clicks are closer together, but they get increasingly farther apart from each other, right? Ba, ba. Right? So the pitch is decreasing or increasing. And then you can do the same on B.
B,
Going up,
B.
going down. Spectral property is roughly the same, right? So the point is that these are really, really equivalent processes, okay? And so the same thing happens in whales. We show that the A vowel can have 1 + 1 + 3 type or 5R type, and the I vowel has 1 + 1 + 3 or the 5R type, right? So just like in Mandarin, you can have two tones or on Ba and B, you can have the A vowel and the I vowel on 1 + 1 + 3 or 5R on any other coda type. Also, they exchange these vowels in conversations. So here's what we describe a conversation. So back in the day, this would be just considered 1 + 1 + 3, exchange just the same type. They're just exchanging the same type. But if you look at the spectrum, this new dimension, you see that there's actually different types that they're exchanging and in these conversations. And finally, with a little bit of digging, we realized, well, this is actually also produced extremely similarly than human vowels. Okay, now I'm repeating myself, but we have vocal folds that are vibrating, and we have the vocal tract, okay? So these are vocal folds, vocal tract when we speak. They have direct equivalent, right? So the phonic lips are their vocal folds. That's the thing with which they click. And the cool thing is that on top of the phonic lips, they have the distal air sac. And the distal air sac is the thing that they change the shape of to get those spectral patterns, okay? So this is a case of convergent evolution. These things are not evolutionary connected, but basically they have the exact same function. Okay, now we wanna, this is something, so some of this thing is actually not even in the preprint, because I was doing some extra work and there were some other things that not only show that that there are similarities between vowels and codas, but also that they behave very similarly, the codas and the vowels. Not only they have formas, but they also behave similarly. So the first click in a coda, so there's the idea of their subcoda structure. The first click of a coda appears to have a special prominent function, okay? And that's also the case in humans. What we observe, if you put these codas in an array, is that sometimes the first click is much higher, okay? Has a much higher spectral frequency. And that's across the whales, fork, Atwood, some of you know these whales, right? So the first three codas, longish codas, have first click higher, but that this one's flat. Same with fork, but the third one has a flat coda. This is roughly how it sounds. You won't be able to hear this with the naked eye. Fork again, right? Fruit, really high. See, I mean, if you don't see well there, you can see on the screen, really high, really prominent first click. You can't miss this. I mean, this is like, it goes right into your eye when you look at these properties. And sometimes, but more rarely, the first click is low, okay? So here you have Atwood, TBB, and Algene. You have the first click that appears much lower. So that's interesting. So the first click appears to have a prominent position in codas. It's optionally high, optionally low, or most of the time flat. And what we observed is mostly on longish codas, which is interesting. So there's some distributional pattern. Now, this is highly reminiscent of something we have in the way we humans perceive consonants, okay? So when we say, how do we perceive consonants? We talked a lot about vowels, but humans also have consonants. So b, g, and d are consonants, right? But b, d, and g are not really easy to hear without the vowel. If I only say consonants are basically silence. At least these stops are basically silence. So the way we hear the difference between ba and pa and ga is looking at the spectrum of the vowel. And actually, more specifically, looking at the first few clicks or the first few periods of the spectrum of the vowel. For example, there are three words here: a bab, a dad, and a gag. And you see that the biggest thing that distinguishes them is this first couple of clicks or vocal fold vibrations at the beginning of the vowel, right? So for b, the spectrum, this band of frequency goes down. For g, it's a little flat, and for g, it's high and goes down, right? So something is very similar to optionally first click being high, low, or mid. Okay, so these are our human ways to distinguish vowels. Okay, back to the vowels. Another behavior in the vowels that we observe is very similar is also co-articulation. Now, this is a complex linguistic term, but I want you now all to say two words. I want you to say ebi and eba. And I want you to pay attention to where your tongue is when you say an e. So ebi, eba. Did you feel your tongue being much more towards the back when you say eba versus ebi? During the e, you were not saying a or e, you were anticipating what you're going to say, okay? We are anticipating what we're going to say. So our tongue in eba, ebi is much, when we say an ebi, it's much fronter because it's going to have to be front in the next syllable. When we're to say eba, it's fine to have it a little bit further back. And e. I even recorded myself saying ebi, right? You see, these bands of frequencies are slightly more further apart than these bands of frequencies. So here, when I say eba here, you see this band is already trying to approximate what I'm gonna say for an ah. Ebi, eba. This is me. And this is something also very similar to what we observe in first clicks. This was slightly more difficult to observe, but what happens is, as they're exchanging ahs and e's in conversation, sometimes the first click of the next vowel carries over the type from the first vowel, but only the first click. So first click has some special position. And again, this really, I think you'll have to go watch there. So here is an outward saying ah and then e. And ah has 5 clicks. They're all nice A type. And then for e, you have two bands of frequencies here. But the first click actually has a single-ish peak, okay? Right, so if you analyze the spectrum, this is a nice ah. This is still an ah, although it should be an I. It should be 2 peaks. And then this one has 2 peaks, okay? So the first click is a carryover type from the previous vowel. And that mostly we have observed this when they change the vowels. It doesn't happen when the vowel doesn't change. So just like when we say an ebi, we kind of have some spillover, but in the other direction, they have some carryover effects and vowels as well. So this is, again, this is not very common, but it's definitely observable. And Pinchy, obviously, everything is tested in Pinchy. Pinchy has the other way, the other direction as well. So when she says e and then ah, the first click, but only the first click of the ah has 2 peaks. And there are some other further similarities. For example, we can look at the distributional patterns. most of the time, the A coda vowel is more common than the I coda vowel, and we know that in human language we have vowels that are more common than the others. We have these type of first high click, more often attested on long codas, and that's something similar to humans, where diphthongs are usually longer, so have more flaps of vocal folds vibration and so on. So not only they have similar, these coda vowels have similarity to human vowels in terms that they have form and frequencies, form and bands, that they're produced in a similar way, but they also behave in a similar way when they need to articulate them. And the nice thing about it is that basically you can just look at raw data here. You don't need any analysis whatsoever. So hopefully this talk introduced some evidence that there are subcoda spectral structures, that some codas, some clicks have more prominent positions, which is similar to what happens in humans, and that there's co-articulation in whales as well, which is a well-known phenomenon in human language that also results in phonology and the rules that we have in language and so on. Basically, we were able to our model, our artificial baby language learner, predicted these spectral properties. It didn't describe them for us, but it predicted them for us. And we can confirm them with really basic analytical tools. And more importantly, we're showing that exact same tools that we use for human language actually works for whales. So we use the same software, we use the same linear predictive coding to distinguish between those types. We use the same source filter theory that was devised in the 50s for human language. And there's something we need to not forget is that, yes, models are great, but the crucial part is that we look at the data, and good old philological work where you just stare at the data for hours upon hours is very important. So there's like a really strong case for AI interpretability where it can basically help act as a tool to accelerate insights, but human researchers is still necessary. And finally, I want to conclude with this something that I started at the beginning. I think it's really exciting time because we have three intelligences now, or at least three types of intelligences, if I can divide things a little bit. We have the humans, we have the AI, and we have the animals, and they're all mutually informative. We can learn about how humans learn language with building these artificial baby language learners with all-purpose neural nets. We can learn about their language acquisition from our language acquisition, right? We have steps, we have data with mother-calf pairs and so on. So they're like, taking all these three players now seriously, I think, can bring a lot of new and exciting insights. Thank you.
This is so cool. I'm blown away by this, Gašper. So quick question related to the vowels. And in humans, if I sort of know, going back to the source filter representation of speech, if I know the sort of geometry of my vocal tract, then I can predict Helmholtz resonances, and I can sort of predict where those form. So can I do the same thing? Yeah. And would they match up with where you're seeing these formants in whales?
That is an excellent question. So in acoustics, we have the tube model, right? The tube is, but it's the best approximation for our vocal tract. So when you say an your vocal tract looks the most like as a simple tube, and it's very easy to model where resonant frequencies are going to be in a tube. And there's a lot of work in the 60s, 70s that created the model of human resonances and so on. So for whales, we have much poorer understanding of how this air sac actually works. But there is some good news, which is that we see multiples of resonances in the A type, which suggests that this is also that a tube model would also be a good approximation. What is more difficult is where they're getting that second. So the I vowel is more difficult, but there are ways it could be a Helmholtz resonator thing. they're different. I mean, but these are speculative at this point because its magnitudes more harder to know anything about the articulation compared to humans, right? The really important thing to me when I was looking at their articulation is that the phonic lips are at the entrance. When I read that the phonic lips are at the entrance of the distal air sac, I was so happy because this is vocal folds plus vocal tract, right? But we have an idea of how the air sac is, but it's much poorer than the humans.
Hi, Gašper. Phenomenal insight. Thank you. I'm intrigued by one thing. So you did extremely detailed analysis instead of in terms of the production, but the hearing apparatus is very different in whales and in humans. And so the whales have evolved to interpret those clicks as echolocation echoes, right? And so if I were to send a perfect click, okay, it bounces off you, and the thing that comes back is a deformed click, okay, that conveys your image. If a whale was able to distort the click to match what it hears from an echo, okay, it would then literally say Gašper, okay, it would be a visual ideogram, okay, but acoustically, right? So I'm wondering how many have you thought of in terms of how they normally range and what kinds of echoes they have? What are the degrees of freedom you have in that? And what would those clicks look like if you try to interpret them as echoes from an object? So geometrically.
That's great. There are several issues, I think. Thanks for your question. So first of all, none of these are echolocation clicks. These are coda clicks that are actually acoustically quite different from echolocation clicks. So we speculate that for echolocation, they click, and the click travels through the spermaceti organ onto the junk organ, which are acoustic lenses, and makes it different spectrally because it's much louder. We speculate that these clicks bounce off back and forth within the spermaceti organ, because we see in the clicks, for example, these are echoes within the spermaceti organ. Now, the important thing is that these spectral properties, first I thought, oh, this is they are just changing the shape of the spermaceti organ, and they get this but it doesn't work from a tube model, because the resonances would be much lower, because that thing is 3 meters long, and even though in oil air travels more fast, there's no way we could get like 6,000 hertz resonant frequency in that thing. So it must be that little air sac that is causing these spectral frequencies. In terms of perception, that's an excellent point. And the cool thing is that we have shown that these spectral properties also appear from when a whale that is not carrying the mic was speaking on this mic. So it can be heard. And when we did the birth recording, it was also present there, even though it was just underwater microphone. It's likely that there's a loss of some of the spectral properties. But the thing is, I as researcher need to have crystal clear spectrum in order to be able to say there's a pattern here. So the level of the proof is much higher when I'm describing the communication system compared to a whale who is listening another person talking, right? So even if you distort my signal, you'll be able to decode me quite a bit. But the cool thing is that this is perceivable and well within the range of hearing. I mean, they can hear up to 35 kilohertz, probably. At least that's what we think. Probably even much more, but at least 35, and this is all below that. And this is just, again, these cues that I'm seeing just like in vowels, I and E, right? We see the most prominent cues, but there are a million other phonetic properties that distinguish them. For example, I is usually longer, and we speakers pay attention to those things as well, because nature wants the signal to be capable, and so there to be many ways to distinguish I and E. So that's within, but it's a very interesting question, and I think we know about their audition even less than we know about their sound production.
Yes, I mean how they actually image whatever they hear in clicks. Okay, even though they are not emitted as echolocation clicks. Okay, the apparatus that hears it, okay, yes, hears them as, I mean, they have the intensity of the echoes, right? So maybe they parse them in more in a visual way, okay? They parse them in terms of shapes.
And for example, another really interesting implication for this is, I know when you say an ah, I can distinguish your ah from David's ah, right?
Of course.
But those are minuscule differences, but I'm very good at that as a human, and they're probably good at that as well. So one thing that they have is this duration of this echo tells you how big you are. So they could use this as a cue, as a cue for distinguishing different males. But this has proven to be quite challenging, a metric. So maybe there's stuff in the spectrum that we're not even observing yet that carries that information.
On that size thing, I don't know how much data you have that is, say, of calves. Do you see a difference between, like, if you've got any information on age ranges, does this ability to make an A or an I, E, does that change over time, over the life of the animal?
So the thing is, there are a couple of complications. First, you need tag recording, and first you need to tag a calf. So that's first complication. Calves are less chatty than the adult whales are. So we have some data, but we're looking actually, I mean, this would be the best. And the other thing that would be really cool is to see if other, like Galapagos or Azores, have different, because vowels are extreme. Like you can just by answering hello, I can locate you and locate many things about your social identity. And so vowels are very prone to this kind of social identity in humans. So it'd be interesting to see if there's anything similar in whales as well.
I thank you for the great talk, really mind-blowing. I think maybe I missed something, so just a clarification. So what proportion of the vowels, let's say the codas that you found in your data, you could classify as either A or E type? So all of them. So
well, there are some noisy one. I would say we just did that. I just manually did it, and we did it also with LPC. I would say about there's about 10 to 15% that is like I had a trouble. So but otherwise, you just take a pen and you just annotate them. It's quite easy to see.
So we could like basically classify codas into two main categories, and then within these two main categories, you go on and you look for patterns like along the lines of consonants, what you were arguing, and then you could find more complexity.
We have a really nice bimodal distribution of how much spectrum goes up and down. One distribution is very little, so those are monophthongs or level vowels, and then one is much more, which is rarer and usually on longer codas. But then you see these nice patterns. I should say diphthongs are quite rare, and mostly on the A type. I type has questionable diphthongs.
Thank you.
Thanks. Awesome. Unsurprisingly, thank you. I was just going to add that most of these coda conversations actually happen within a body length or two. So a lot of these dyadic or triadic, like duets, choruses, exchanges happen very close proximity. So likely detection of this is pretty good. Brian, we're working on the calf data set now. And I would add something that Gašper left out, which is this primarily focuses on the coda types that had sort of previously been identified. And there are these longer ones called coda creeks that can be 18 to 25, 28 clicks long that traditionally have been ignored for work time limitations mostly. And I think looking at these patterns in those longer creeks is where it's going to get really interesting. Anyhow, I just wanted to add all that.
Last one over to Tom.
And great talk. I was curious with the baby model for sperm whale production. Seems like the choice of code input to the generator could have some real effect on what the system's doing. And similarly, like choice of the discriminator might have a real effect on like what are the parts that the generator thinks is important to replicate well. And so I'm curious how you're thinking about that. What's the input? How do you avoid bias from the rest of the system?
So we showed that. So there's a prior on how many classes you give to the generator to be able to work with, but it's not really, because while these are binary codes, in effect they're actually continuous variables, and we've shown that even in language, even if there's a mismatch between classes and the actual classes, the learning still happens and you still can get informative information. So that's a nice thing. I mean, these are very the thing with GANs is that the audio quality is horrible, but they are extremely robust learners because they need to learn by they never see the data, so they need to create all their data on their own. And then they need to basically learn the entire internal grammar, to generate.
But I guess, so the input for the generator, are they like VAE codes, or are they like handwritten?
Just a bunch of uniformly distributed variables.
Okay.
So like 95 minus 1 to 1, and then a few binary codes. Very, very tiny, like even compared to autoencoders, a tiny latent space.
Okay.
Thank you, Gašper. I just also want to make a point that how unusual it is to have a linguist kind of at an ocean-related conference, and kind of really highlights the interdisciplinarity now that we're beginning to see in ocean science and marine biology and animal communication, which is really, and also just to kind of give a one, it was last June, we lost our principal advisor, Roger Payne, who discovered that whales sing. And in one of the first meetings where we had, Roger said, "I can't believe I went my whole career without working with a linguist." So yeah, anyway, thank you.
Thanks.
So we're now going to change gears to plants, just to kind of keep stretching us into different dimensions. And we're going to go to the live stream for Lingak.